During the Industrial Revolution, Sadi Carnot asked the question, how efficient can a steam engine theoretically be? To answer this question, he represented the steam engine more abstractly as a heat engine, where the flow of heat is converted to useful mechanical work. He then concluded that the most efficient heat engine is the one that is reversible. Rudolf Clausius analyzed these findings in more detail. Whereas Carnot believed the flow of heat generates useful work, just like the flow of water makes a water wheel turn, Clausius proposed that heat energy itself is converted to mechanical energy. Moreover, he quantified the degree to which a system has irreversibly transformed by introducing the concept of entropy. Ludwig Boltzmann explained these findings of Clausius in the framework of statistical mechanics. By modeling a gas as a large number of randomly moving molecules, he explained the connection between temperature and mechanical energy, and he related entropy to the statistical likelihood of molecular configurations. These concepts can be used to derive the Maxwell-Boltzmann distribution, which tells you at which velocity gas molecules move if the gas has a certain temperature. With Boltzmann's statistical mechanics, the relation between temperature, or internal energy, and mechanical energy was now understood. However, it still leaves us with the question how the two are related to the energy in radiant heat, which is, like light, electromagnetic radiation. This led to the study of blackbody radiation, which is the spectrum of electromagnetic radiation that is emitted by an object with a certain temperature. Wilhelm Wien derived an expression for the spectrum of blackbody radiation, based on the molecular kinetics as derived by Boltzmann. After all, it was known that moving charges radiate electromagnetic waves, so it makes sense to connect the radiation spectrum to the velocity distribution of the molecules. Even though the radiation law that Wien derived matched well with experimental observations at that time, later measurements in the deep infrared wavelength regime revealed a clear mismatch with Wien's formula. Max Planck initially tried to derive Wien's radiation law from considerations based on entropy rather than molecular kinetics. Initially, he thought he succeeded in finding such a derivation, but when the failure of Wien's law became apparent, Planck had to adapt his derivation to fit the new measurement data. To give a theoretical justification for this new derivation, he used Boltzmann's statistical mechanics with the assumption that the energy which is distributed over the radiating oscillators is quantized in discrete packages. This derivation of Planck's radiation law is often considered the starting point of the development of quantum mechanics. In the following, we're going to look how quantum mechanics was developed in its early stages. Many different areas of physics contributed to this development. One such area of physics is thermodynamics and statistical physics. We already saw the role it played in the development of Planck's radiation law, which is seen as the starting point of the development of quantum mechanics. Later, Albert Einstein frequently used arguments from statistical mechanics to argue that radiation is quantized. He noted that the formula for entropy of radiation looks like that of a gas consisting of discrete particles. Moreover, he used the quantum hypothesis to explain observations of heat capacities at low temperatures. Later, he connected Planck's radiation law to kinetic theory by assuming that light quanta carry and transfer momentum, and that the emission of radiation can either be spontaneous or stimulated by incident radiation. Other contributions to the early development of quantum mechanics came from the study of atomic structure and subatomic particles. The study of cathode rays led to the discovery of electrons and X-rays, which are used to obtain information about atomic structure. Similarly, alpha, beta, and gamma radiation indicate what atoms consist of and what processes occur inside atoms. The obtained insights led to Niels Bohr's model of the atom, which states that the atomic energy levels are quantized. Scattering theory plays an important role in probing subatomic structures, even to this day. By shooting many tiny particles at many tiny targets, and seeing what comes out after the subatomic interactions, one can infer what interactions must have taken place. By shooting alpha particles at gold atoms and seeing how they are scattered, Ernest Rutherford inferred that the atom must contain a tiny nucleus around which the electrons move. Moreover, Arthur Compton inferred that X-rays must have a quantized nature by looking at how they are scattered by electrons. Many insights were obtained using tools, observations, and ideas from optics. With spectroscopy, one can measure which wavelengths of light are emitted and absorbed by different materials, which allows us to study the energy levels of atoms, which in turn reveals how atoms are structured. In Compton scattering, spectroscopy is used to measure how the wavelength of X-rays change after they are scattered by electrons. Einstein's model for solids explains how properties of heat capacity are related to properties of optical absorption, thereby allowing for a convincing experimental verification of the model. When Louis de Broglie tried to explain the particle-like properties of radiation and the wave-like properties of matter, he drew inspiration from optics. Light can be modeled as rays with a definite position and direction, but they are modeled more accurately as light waves. Similarly, matter can be modeled as particles with a definite position and direction, but it should be modeled more accurately as matter waves. Also, several developments of quantum mechanics required knowledge of Einstein's special theory of relativity. Note that different aspects of quantum theory were accepted at different times. Einstein's proposal that molecular vibrations are quantized to explain the observed heat capacities at low temperatures was the first quantum hypothesis to be widely accepted. The idea that atomic energy levels are quantized was accepted sometime later. However, the idea that radiation itself is quantized, as Einstein proposed in 1905, wasn't widely accepted until the discovery of Compton scattering in the early 1920s. The idea that radiation is quantized was proposed by Einstein in 1905. He understood that this would appear in conflict with the well-established wave theory of light, but he remarked that the two could still be consistent with each other because in optics we only observe time averages, where quantization would not be immediately apparent. Einstein presented several arguments for the quantization of radiation. The first argument is that the formula for entropy of radiation resembles the formula for entropy of a molecular gas. To see this, recall Planck's radiation law for the radiation energy density. In the limit of high frequency or low temperature, this law can be approximated by Wien's radiation law. We rewrite this expression to solve for 1 over temperature, which we know from thermodynamics equals the derivative of entropy with respect to energy. Thus, by integrating with respect to energy density, we find an expression for the entropy density. The total entropy and energy can be calculated from the entropy density and energy density. We can now write a formula for the entropy of radiation in a certain volume, and we can calculate how the entropy changes if we change the volume by a certain amount. Having obtained an expression for the entropy of radiation, let's now compare it to the entropy of a molecular gas. According to Boltzmann's statistical mechanics, the entropy is determined by the number of microstates that result in the most likely macrostate. When the system consists of a large number of molecules, this can be considered equal to the total number of possible microstates. So if we have n molecules, which each can occupy some position in a volume V, then the total number of microstates is proportional to the volume raised to the power n, the number of molecules. From this expression, we can calculate how the entropy changes when we change the volume of the system. When we compare this expression to the expression we found for the entropy of radiation, we find that the two are equal if the radiation consists of n particles, each with an energy equal to Planck's constant h times the frequency f. Of course, if two formulas look similar, it doesn't necessarily mean that they describe the same physics. So Einstein presented more arguments based on experimental observations to argue for the quantized nature of radiation. One such experimental observation is Stokes' rule. This rule states that if a fluorescent material is illuminated with light of a certain wavelength, then the emitted light must be of a longer wavelength. Why would this have to be the case? If we write this inequality in terms of frequency, and we use Einstein's proposed relation that a photon's energy is proportional to its frequency, then Stokes' rule is basically a straightforward consequence of energy conservation. The outgoing energy cannot be larger than the input energy. Another experimental observation that Einstein explained with the quantization of radiation is the photoelectric effect. It was observed that if you shine light on certain materials, they can emit electrons. Whether electrons get emitted or not turned out to depend on the frequency of light. If the frequency exceeds a certain threshold, then electrons get emitted. However, if the frequency is below that threshold, then it doesn't matter how much light you shine on the material, no electrons get emitted. The intensity of light turned out to determine the number of emitted electrons, provided the light's frequency is sufficiently high. Why should the emission of electrons depend on the frequency of light? And why should the number of emitted electrons depend on the intensity? Einstein provided the following explanation. Light is quantized, and each quantum of light has an energy of Planck's constant times the frequency. For an electron to be expelled from the material, this photon energy should exceed some threshold energy called the work function, which can be different for different materials. Therefore, the frequency of light must exceed a certain threshold value before electrons get emitted. Light which is more intense consists of more photons, so more electrons can get emitted. Therefore, the number of emitted electrons depends on the intensity of light. Based on this model, Einstein made the following prediction. A photon can release an electron if the photon's energy exceeds some minimum energy called the work function. Because the photon's energy depends on its frequency, only light of a certain minimum frequency can release electrons. The kinetic energy of the released electrons equals the photon energy minus the energy that was required to release the electron. Therefore, if we plot the kinetic energy of the released electron as function of the light's frequency, we expect a linear function, whose slope is equal to Planck's constant. Different substances may have different work functions, but the slope of the linear function should be independent of the substance. This prediction was verified experimentally by Robert Millikan in 1914, but Einstein's light quantum hypothesis was still not accepted in spite of this result. Another argument that Einstein presented for the light quantum hypothesis relates to the ionization energy of gas molecules. Gas molecules can be ionized via two different methods. The first method is electron bombardment. Consider a gas molecule that consists of positive and negative charges, resulting in a net zero charge. To ionize the molecule, we generate electrons with a heated filament, and accelerate the electron by applying a voltage. The kinetic energy of the electron is given by the electron charge times the applied voltage. By varying the voltage and observing when the gas gets ionized, one can infer the ionization energy. The second method to ionize gas molecules is to expose them to radiation. If the wavelength of the radiation is short enough, the molecule will be ionized. So we have two different methods to ionize gas molecules. The two methods give roughly the same result for the ionization energy if we assume that energy of a quantum of radiation is given by Planck's constant times the radiation frequency. The minimal ionization potential for air was measured to be around 10 volts, and the maximal ionization wavelength for air was measured to be around 200 nanometers. If we plug these values in the formula for the electron energy and the hypothesized formula for photon energy, we find similar values for the ionization energy. We started out by saying that Planck's radiation law is widely considered to mark the beginning of quantum theory, because to derive the formula, one has to assume that energy comes in discrete packets of Planck's constant times the frequency. However, Among the arguments that Einstein presented for the light quantum hypothesis, he did not mention Planck's law as evidence for the hypothesis. Rather, when he compared the entropy of radiation to the entropy of a molecular gas, he used Wien's approximate law rather than Planck's law. Einstein thought at the time that Wien's law implied particle-like behavior of light, and that when Wien's law is not valid, light may not show particle-like behavior. When Einstein mentioned Stokes' rule as an argument for the light quantum hypothesis, he also mentioned cases where he thought Stokes' rule may not be valid. He expected that there may be deviations from Stokes' rule when using radiation of a wavelength for which Wien's law is not valid. Einstein recognized his oversight in the following year. He mentioned that he worked out his arguments under the assumption that Wien's law is valid, and that Planck's law would imply exceptions to his arguments. However, he now realized that Planck's radiation law also assumes the light quantum hypothesis. In the following year, Einstein applied the quantum hypothesis to explain observations concerning the specific heats of materials. First, let's recap some important concepts from statistical mechanics. Suppose we have some system which can be in different states with different energies. This system is in thermal contact with a reservoir of temperature T. This means that the system and the reservoir can exchange energy in the form of heat, so that the temperature of the system stays constant, but no change in the amount of particles or volume of the system can occur. The probability that the system will be in a certain state S is, according to statistical mechanics, determined by the Boltzmann factor. The collection of all possible system states S and their probabilities P of S is called the canonical ensemble. In our case, the system is a one-dimensional harmonic oscillator which oscillates in the x direction. The oscillator can vibrate a lot, or it can vibrate only a little. These are the different system states S, which each have an energy E of S. The energy is given by the sum of the kinetic energy and the potential energy that is determined by the spring constant. Using the Boltzmann factors, we find the probability that the oscillator has a certain displacement x and momentum p. From this, we want to calculate the probability that the system has a certain energy E. To find this probability, we need to know how many states xp have the same energy E. This gives the density of states G of E. We see from the expression for the energy that states with the same energy E describe a circle with radius square root E in phase space. The number of states with energy between E and E plus dE is thus given by the circumference of the circle times the circle width. When we rewrite d square root E in terms of dE, we find that the density of states is constant and does not depend on the energy E. Now that we know the probability that the system has a certain energy E, we can calculate the average energy of the system. We find that the average energy of a one-dimensional harmonic oscillator is Boltzmann's constant times the temperature. This is consistent with the equipartition theorem that states that each contribution to the energy, which in this case are the kinetic energy and the spring potential energy, carries 1/2 kBt units of energy. If we now consider an atom in a three-dimensional lattice, it can oscillate in three different directions. So the average energy of a single oscillator should be 3 kBt. Experimentally, this fact should manifest itself in the heat capacity of solids. The heat capacity tells you how much heat energy you should add to raise the temperature by a degree. So if we take the derivative of the internal energy U with respect to the temperature T and divide by the number of atoms N, then we find that per atom the heat capacity should be 3 times Boltzmann's constant. This is known as the Dulong-Petit law. However, it was observed experimentally that this law is only valid for sufficiently high temperatures, but at low temperatures the heat capacity drops to 0. The failure of the Dulong-Petit law at low temperatures was one issue that Einstein aimed to resolve with the quantum hypothesis. The other issue had to do with the number of degrees of freedom, which according to the equipartition theorem directly determines the heat capacity. To arrive at the Dulong-Petit law, it was assumed that an atom can oscillate in 3 dimensions. Taking into account the contributions of the kinetic and potential energy, we conclude that the internal energy consists of 6 contributions of 1/2 kBt. However, experiments with optical absorptions revealed that the atom ions vibrate at infrared frequencies, but the electrons can also vibrate, namely at ultraviolet frequencies. This means that electron vibrations constitute additional degrees of freedom, which, according to the equipartition theorem, should also contribute 1/2 kBt units of energy. This should result in a heat capacity that is much higher than predicted by the Dulong-Petit law. Now let's examine the model that Einstein proposed to resolve these issues. He proposed that if an oscillator oscillates at some frequency f, it can only do so at discrete energy levels, which are integer multiples of Planck's constant times the frequency. Mathematically, it means that the density of states can be described as a sum of delta functions. Recall that we previously calculated the average energy of a one-dimensional oscillator and found it to be equal to kBt. If we now redo the calculation, but assuming discrete energy levels, we find a different expression for the average energy, which now is a function of frequency. We can verify that if we make Planck's constant very small, so the energy levels become continuous again, then we can approximate the exponential in the denominator, and we find that the average energy is the same as we calculated previously. Also note that from this expression for the oscillator energy, Planck's radiation law follows. Having found the average energy for a one-dimensional oscillator, we can find the average energy for a three-dimensional oscillator by multiplying by 3. To find the heat capacity, we differentiate with respect to temperature. If we plot this function for a certain optical wavelength or frequency, we find that indeed the heat capacity goes to 0 for low temperatures and satisfy the Dulong-Petit law for higher temperatures. Moreover, if we decrease the wavelength or increase the frequency, we see that for more temperatures the heat capacity is negligible. This explains why the electron vibrations, as observed in the optical absorption experiments, do not contribute to the heat capacity, contrary to what the equipartition theorem would predict. So in summary, the Einstein model for solids connect optical absorption properties, heat capacities, and Planck's radiation law. Einstein's explanation for the vanishing specific heat at low temperatures was well received by the renowned chemist Walter Nernst. He became convinced of the logical power of quantum theory. In the invitation letter to the first Solvay conference, it is mentioned how experimental observations contradicted classical theory, and how Planck and Einstein resolved the contradiction with the principle of energy quanta. However, while Einstein was commended for his work on specific heats, the relation to optical properties, and the photoelectric effect, he was forgiven for missing the mark with his hypothesis of light quanta. The quantization of atomic vibrations was accepted, but the quantization of radiation was not. The next development in quantum theory came with the study of atomic structure. Niels Bohr proposed in 1913 a model of the atom where electrons can only have certain orbits around the nucleus. These orbits are defined such that the angular momentum of the electron is an integer multiple of the reduced Planck's constant, which is Planck's constant divided by 2π. If an electron loses energy by dropping from a high-energy orbit to a lower-energy orbit, it emits light with a frequency such that the energy change equals Planck's constant times the frequency. To better understand the context and significance of this model, let's first give an overview of the history of atomic theory. The first serious proposal for atomic theory in modern times came from John Dalton in the beginning of the 1800s. Based on the mass ratios with which two different substances react to form a third substance, he concluded that substances are composed of indivisible atoms of different elements. For example, 100 grams of carbon can react with 133 grams of oxygen to form one sort of oxide, or it can react with 266 grams of oxygen to form a second sort of oxide. Note that the ratio 266 to 133 reduces to 2 to 1. The fact that such ratios reduce to ratios of small integers is known as the law of multiple proportions. The interpretation is that the carbon atom can react with either one oxygen atom or two oxygen atoms. Several years later, William Prout hypothesized that the atomic weights of different elements are integer multiples of the lightest atom, hydrogen. For example, the weight of helium is 4 times the weight of hydrogen. The weight of carbon is 12 times the weight of hydrogen, and oxygen is 16 times the weight of hydrogen. These weights can be inferred from the masses with which different atoms react. Returning to our previous example, if 100 grams of carbon reacts with 133 grams of oxygen, and we assume that one carbon atom reacts with one oxygen atom, we know that the ratio of the weight of an oxygen atom to the weight of a carbon atom is 133 to 100, which is basically a ratio of 4 to 3. By figuring out different ratios in this way, the weights of all atoms can be rewritten in terms of the weight of a hydrogen atom. However, Jöns Jacob Berzelius found a counterexample to Prout's hypothesis. The atomic weight of chlorine was experimentally measured to not be an integer multiple of hydrogen's atomic weight. In the second half of the 1800s, Dmitry Mendeleev ordered the elements in a periodic manner, according to their chemical properties. This ordering is known as the periodic table. The elements are more or less ordered by their weight, with the lightest element hydrogen at the beginning, and then followed by increasingly heavier elements. However, sometimes the order of two elements is reversed, based on the chemical properties. For example, cobalt is heavier than nickel, but cobalt comes before nickel in the periodic table because of its chemical properties. The position of an element in the periodic table is denoted with the atomic number. At this time, the atomic number was interpreted as just an index, without any physical significance. At the end of the 1800s, the electron was discovered through the Zeeman effect and cathode ray tube experiments, and it was understood that these electrons are part of the atom. Thomson's plum pudding model tried to explain what the atom looks like and how the electrons are arranged in it. He believed that the atom was a blob of positive charge, with negatively charged electrons scattered through it, just like pieces of plum are scattered throughout a plum pudding. One can infer how many electrons one atom contains through various experiments. For example, it can be theoretically calculated how much light one electron scatters, which is a process known as Thomson scattering. So by measuring how much light is scattered by a certain amount of gas, one can calculate how many electrons there are. If you know how many atoms there are, by dividing the total weight of the scattering substance by the atomic weight, then you know how many electrons there are per atom. It was found that the number of electrons per atom is about the same as the atomic weight of the atom. However, more accurate measurements revealed that the number of electrons per atom is about half the atomic weight. Ernest Rutherford then found, also via scattering experiments, that the atom does not look like a plum pudding, as Thomson had previously proposed. Rather, the results of the scattering experiment suggest that the positive charge of an atom is concentrated in a tiny nucleus, which is much smaller than the total size of the atom. Meanwhile, Antonius van den Broek hypothesized that the atomic number does, in fact, have physical significance. Namely, it represents the charge of the atomic nucleus. And if the atom has no net charge, it must therefore represent the number of electrons. And indeed, for many elements the atomic number is about half the atomic weight. After Rutherford demonstrated that the atom has a small nucleus, Niels Bohr proposed a model of the atom where the negatively charged electrons orbit a positively charged nucleus. To explain the spectral lines that are observed in atomic spectroscopy, he proposed that the electron can only be in orbit with certain energy levels. When an electron drops from a high-energy orbit to a lower-energy orbit, light is emitted with a frequency that is equal to the energy difference divided by Planck's constant. Henry Moseley gave experimental evidence for van den Broek's hypothesis and Bohr's atomic model via X-ray spectroscopy. He experimentally found a relation between the atomic number of an element and the frequency of one of its spectral lines in the X-ray regime. This relation is consistent with Bohr's model, and it confirms van den Broek's hypothesis that the atomic number of an element has physical significance. The name of Moseley is not as well remembered as those of Bohr or Rutherford. However, his importance is not to be underestimated. Bohr said in an interview weeks before his passing that only after Moseley did people take the work of Rutherford and Bohr seriously. However, Moseley died at the young age of 27 during the First World War in Gallipoli. Isaac Asimov remarked that his death may have been the most costly single death of the war to mankind, and that Moseley almost certainly would have won the Nobel Prize had he lived. Through the X-ray spectroscopy experiments, it became easy to sort elements in the periodic table, as sorting by atomic weight was not always reliable. Moreover, it helped identifying gaps in the periodic table, which led to the prediction of an element with atomic number 72, which is now known as hafnium. So it has now been demonstrated that the atomic number, which is an integer, has physical significance. Proud's hypothesis already anticipated that integers would have physical relevance. However, it appeared to have been disproven experimentally by Berzelius. In 1920, Francis Aston shed light on the situation with his whole number rule. He found that elements may come in different isotopes, which have different but integer atomic weights. For example, the non-integer atomic weight of chlorine is a result from the fact that it comes as a mixture of two different isotopes with integer atomic weights. When James Chadwick discovered the neutron, a clear understanding of the constituents of the atom began to form. The mass of an atom is mainly located in its nucleus. The nucleus consists of positively charged protons and neutrons which have no electric charge. The atomic mass number is given by the amount of protons and neutrons, while the atomic number is given by the number of protons. An element is defined by its number of protons, but can have different integer atomic masses depending on the number of neutrons. This description of the atomic structure seems simple enough in hindsight. However, this historical overview serves to remind us that figuring out such a simple picture and demonstrating that it indeed describes reality is far from trivial. Let us now look at some of these developments in more detail. First, we'll discuss the discovery of the electron. There were several lines of study that contributed to the development of the electron model, including observations in chemistry, cathode ray tube experiments, and the Zeeman effect. J.J. Thomson investigated in 1897 the rays observed in a cathode ray tube. He believed that these rays consisted of charged particles, which we now know to be electrons, and he determined their charge-to-mass ratio in the following way. Suppose we have an electron moving at some velocity v. If we apply an electric field perpendicular to the electron's direction of motion, that field exerts a force on the electron, so that the electron is deflected. The magnitude of the electric force is equal to the charge of the electron times the magnitude of the electric field. Now suppose that at the same time we also apply a magnetic field, in such a way that it exerts a force in the opposite direction. The magnitude of this force is given by the magnitude of the magnetic field times the charge of the electron times the speed of the electron. The strengths of the electric and magnetic fields can be tuned in such a way that they cancel each other out, so that the moving electron does not get deflected. By equating the magnitudes of the electric and magnetic forces, we can solve for the electron speed, which turns out to be given by the ratio of the electric field and magnetic field. Now that we know the speed of the electron, we can perform a second experiment to determine its charge-to-mass ratio. We apply a magnetic field to the electron such that it is deflected. The magnetic force will always act perpendicular to the electron's direction of motion, so the electron will move in a circle with a radius r, which we can measure. We know that the centripetal force that causes circular motion is given by the mass times velocity squared divided by the radius of the circle. In this case, the centripetal force is the magnetic force, so we can equate the expressions for the magnetic force and the centripetal force. By equating them, we find an expression of the electron's charge-to-mass ratio in terms of quantities which are all measurable. The value that is found for the electron's charge-to-mass ratio can be compared to the charge-to-mass ratio of the hydrogen ion, which had already been deduced from experiments in quantitative electrolysis. In such an experiment, we have hydrochloric acid, which is hydrogen chloride dissolved in water. If we introduce two electrodes to which we apply a potential difference, then the positively charged hydrogen ions will be attracted to the negative electrode, where it will gain electric charge and form hydrogen gas. Similarly, the chlorine ions will form chlorine gas at the positive electrode. If we perform this process for some time t, and with a current I, then the total charge that is transferred from the electrodes to the ions is given by I times t. We can measure the mass of the hydrogen gas that is generated during that time. We can then calculate the charge-to-mass ratio of the hydrogen ions by dividing the transferred charge by the generated mass of hydrogen gas. If we know the mass of a hydrogen ion, we can also calculate the charge of a single hydrogen ion. When the charge-to-mass ratio of the electron is compared to that of the hydrogen ion, it turns out that the electron's charge-to-mass ratio is 1836 times higher than that of the hydrogen ion. If we assume that a hydrogen atom consists of a positively charged hydrogen ion and a negatively charged electron, then the charges must be equal in magnitude to make the atom neutrally charged. It would then follow that the electron is 1836 times lighter than the hydrogen atom. The other method to determine the charge-to-mass ratio of the electron was via the Zeeman effect, which was observed 1 year before Thomson's electron experiments. To observe the Zeeman effect, a light source is put in a magnetic field. The light that is emitted is reflected from a curved diffraction grating, so that different wavelengths are focused at different positions. Each wavelength forms what is called a spectral line. It was observed that when the magnetic field is applied, the spectral line is broadened. However, upon more careful examination, it was found that the line is not quite broadened, but rather split into 3 separate lines. What is the cause of this splitting? Hendrik Lorentz came up with the following explanation, making use of the electron hypothesis. He assumed that an electron in the atom can oscillate freely in 3 dimensions with a certain frequency. These oscillations can be described mathematically using Newton's second law, where the force is proportional and opposite to the electron's displacement. The resulting differential equation is solved by a displacement which oscillates harmonically with some angular frequency omega 0. In the Zeeman effect, we apply a magnetic field. So let's see how the equation of motion changes when we introduce a magnetic field. Let's consider the expression for the Lorentz force, which is the force due to a magnetic field that acts on a moving charged particle. We can include this extra force in the equation of motion for a harmonic oscillator. Without loss of generality, we assume that the magnetic field is pointing in the z direction. If we now write the equations of motion for a harmonic oscillator in a magnetic field for all 3 dimensions separately, we find that the equation for the z direction is not affected by the presence of the magnetic field. For the x and y directions, we end up with 2 coupled differential equations. Let's examine these 2 equations more closely. If we only consider the part of the equation that describes the harmonic oscillation, and ignore the effect of the magnetic field, then we can write down two solutions. In one solution, the electron rotates counterclockwise with angular frequency omega 0, and in the other solution, the electron rotates clockwise with the same frequency. If we now apply a magnetic field in the z direction, we know that the Lorentz force will point outward for the counterclockwise rotation, and it will point inward for the clockwise rotation. Therefore, we can guess that the solutions to the coupled differential equations will be given by clockwise and counterclockwise rotations, but with angular frequencies that are different from omega 0. So let's define a solution that describes counterclockwise rotation with a to be determined angular frequency omega minus. If we plug this solution into the coupled differential equations, we find that indeed the two equations are consistent with each other, because both equations are satisfied when we require that the two constant factors on the two sides of the equation are equal to each other. We can write an approximate expression for the new angular frequency omega minus, which is the original angular frequency omega 0 minus a shift that is proportional to the magnetic field and the charge to mass ratio of the electron. We can repeat this exercise for the clockwise rotation. By plugging the solution into the two coupled differential equations, we see that the equations are satisfied when the two constant factors on the two sides of the equation are equal to each other. We can write the new angular frequency omega plus as approximately the original angular frequency omega 0 plus a shift that depends on the magnetic field and the charge to mass ratio of the electron. Therefore, we see that we can infer the charge to mass ratio of the electron from the frequency shift that is observed in the Zeeman effect. Based on the explanation that Lorentz provided for the observed Zeeman splitting, we can make the following testable predictions. If we apply a magnetic field to the light source, and we look at the emitted light from a direction that is perpendicular to the magnetic field, then we should see three spectral lines. The middle line, whose frequency is unchanged by the magnetic field, should, according to Lorentz's explanation, correspond with electron oscillations parallel to the magnetic field, so in the z direction. Therefore, the light that it emits should also be polarized parallel to the magnetic field, which means that the light of that spectral line should be horizontally polarized. The other two spectral lines, whose frequencies have been changed by the magnetic field, should, according to Lorentz's explanation, correspond to electrons rotating in the xy plane perpendicular to the magnetic field. From our perspective, we are seeing these rotations edge on, which means we see the electron oscillate up and down in the y direction. Therefore, the light of the shifted spectral lines should be polarized vertically. This is called the transverse Zeeman effect, and it is indeed observed experimentally. Now consider the situation where we observe the emitted light from a direction that is parallel to the applied magnetic field. In this case, we cannot see light that is due to the oscillations in the z direction parallel to the magnetic field. Therefore, we cannot see the spectral line with the unaltered frequency omega 0. We only see the two spectral lines whose frequencies have been shifted due to rotations in the xy plane perpendicular to the magnetic field. Since we are observing the xy plane in which the electrons rotate, the light of these shifted spectral lines should be circularly polarized with opposite directions. This is indeed observed experimentally, and it is called the longitudinal Zeeman effect. Moreover, the value of the charge to mass ratio of the electron found by the Zeeman effect agrees well with that found by Thomson's cathode ray tube experiments. All of this provides convincing evidence for the electron hypothesis and Lorentz's explanation of the Zeeman effect. However, Lorentz's model can only explain the Zeeman effect where three spectral lines are observed, but in many other cases, more than three lines are observed. That is called the anomalous Zeeman effect, and that effect was not well explained until quantum mechanics was better understood. Once the electron hypothesis became accepted, it was used to explain several other phenomena. For example, Lorentz used it to explain the optical dispersion of a material. He supposed that incident light makes an electron oscillate, which can be described in an equation of motion that follows from Newton's second law. By solving this equation in the frequency domain, one can solve for the electron's displacement as a function of the frequency of the incident light. The electron's displacement polarizes the atom, which changes the electric permittivity of the material and therefore the refractive index. Thus, Lorentz's model predicts how the refractive index of a material changes as function of the frequency or wavelength of the incident light. Moreover, the Drude model uses the concept of electrons to explain properties of electrical currents, such as Ohm's law. It is also used to explain the Wiedemann-Franz law, which relates thermal conductivity to electrical conductivity. In 1909, Robert Millikan measured the charge of an electron in his oil drop experiment. Oil droplets fall down due to gravity, but if the droplets have a net electric charge, an electric field can be applied to apply a force that counteracts the gravitational force. The magnitude of the electric field that is required to do this depends on the charge of the droplet. Therefore, by figuring out what electric field needs to be applied to make the droplet float, the electric charge of the droplet can be inferred. It was found that the droplet charge was always an integer multiple of the electron charge, which was in magnitude the same as the charge of a hydrogen ion as anticipated. Therefore, combined with the measurement results for the charge-to-mass ratio, it was now confirmed that the electron is 1836 times lighter than the hydrogen atom. Now that the existence of the electron has been established, and we know some of its properties, we can continue to look deeper into the structure of the atom. Thomson proposed the plum pudding model of the atom, where negatively charged electrons are scattered throughout a cloud of positive charge. To investigate the scattering of alpha particles, which are produced through radioactivity, Ernest Rutherford asked Hans Geiger and Ernest Marsden to measure the scattering from thin metal foils. It was expected that the foil would deflect the alpha particles only slightly. However, it was observed that some alpha particles were deflected by very large angles. Rutherford said that it was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. To explain this result, Rutherford proposed that an atom has a large electric charge concentrated in a small volume. This way, an alpha particle can experience a very large Coulomb force when it moves close to this charge. He then worked out the mathematics of such scattering so that he could make quantitative predictions which can be tested in experiment. Before we work out the mathematics of Coulomb scattering, it is instructive to first examine the simpler problem of scattering by a hard sphere. We define the scattering angle as the angle between the direction of the particle before scattering and after scattering. If a particle is reflected by a hard sphere, then the angle at which it scatters depends on the distance called the impact parameter. To find out how the scattering angle depends on the impact parameter, we observe that the particle is scattered according to the law of reflection. The reflection angle equals the incident angle, which is defined with respect to the surface normal. If the sphere has a radius r, we see that the sine of the incident angle is given by the impact parameter divided by the radius. Furthermore, we see that the scattering angle plus twice the incident angle equals 180 degrees, or pi radians. These two equations allow us to write the impact parameter as a function of the scattering angle. The relation can be inverted to find the scattering angle as function of the impact parameter. With these results, we can now define a quantity called the differential cross-section. Consider the case where a particle is scattered at a certain scattering angle. However, in practice, the probability that the particle scatters at that exact specific angle is 0. Rather, we are in practice interested in the probability that a particle scatters within a small range. We want to know which range of impact parameters correspond to that range of scattering angles. This value can be found by taking the derivative of the impact parameter with respect to the scattering angle. This derivative can be calculated straightforwardly using the expression we found previously. Up to this point, we considered the two-dimensional case, where each scattering angle maps to a certain impact parameter, and each interval of scattering angles maps to an interval of impact parameters, which can be found by taking the derivative. However, in practice, the situation will not be two-dimensional, but three-dimensional. When a particle is scattered in three-dimensional space, its direction must be specified with a solid angle, and each finite range of solid angles maps to a two-dimensional area through which the incident particle must have traveled. This small area is called the differential scattering cross-section. Just like in the two-dimensional case, we must first find for each scattering solid angle the point through which the incident particle must have traveled. To find the size of the area through which the particle must have traveled so that it is scattered within a certain range of solid angles, we take the derivative. So let's see how we calculate the differential cross-section for hard sphere scattering. First, let's recall how to specify a solid angle. A solid angle is defined by a point on a sphere with unit radius. This point is described by a polar angle, which traces out a line when it's varied, and an azimuthal angle, which traces out a circle when it's varied. If we define a finite range of solid angles, we define a patch on the unit sphere, which is described by some variation in the polar angle and some variation in the azimuthal angle. The length of one side of the patch is given by the variation of the polar angle. When we vary the azimuthal angle, it traces out a circle whose radius is the sine of the polar angle. Therefore, the length of the other side of the patch is given by the variation of the azimuthal angle times the sine of the polar angle. This gives us an expression for the differential solid angle in terms of variations in the polar angle and the azimuthal angle. If we add up the areas of all patches, we find through integration a total area of 4 pi. This is indeed what we would expect, because this is the area of the sphere with unit radius. To find the differential cross-section, we must, for a given differential solid angle, find the corresponding differential cross-section. For a system that has rotational symmetry, there is no dependence on the azimuthal angle. So we can consider a cross-section where a given scattering polar angle corresponds to a certain impact parameter. To define a differential solid angle, we define a variation in the polar angle, which corresponds to a variation in the impact parameter. We also define a variation in the azimuthal angle. Because of the rotational symmetry of the system, a variation in the azimuthal angle of the scattered particle corresponds to the same variation in the azimuthal angle of the incident particle. We now know, for a certain differential solid angle, the area of the corresponding differential cross-section. Dividing the two gives us the formula for the differential scattering cross-section for a system with rotational symmetry. Recall the relations we found for hard sphere scattering. If we plug these into our formula for the differential scattering cross-section, and use the double angle formula, we find a differential scattering cross-section that is constant for all solid angles. In other words, a hard sphere scatters equally in all directions. As a final sanity check, recall that the differential scattering cross-section tells us for each range of scattering angles what the corresponding area of incidence is. We can add all these areas together to find the total scattering cross-section of the hard sphere. When we perform this integration using the differential scattering cross-section of a hard sphere, we find that the total scattering cross-section is pi r squared. This is indeed the area that incident particles see when colliding with a sphere of radius r. Now that we are familiar with scattering theory, using hard sphere scattering as an example, we can now see how Rutherford used this theory to infer the structure of the atom from scattering experiments. This means we should work out the scattering formulas for a charged particle that is deflected by the Coulomb force. More specifically, we should find the relation between the scattering angle and the impact parameter. The Coulomb force is a central force, and whenever there is a central force, angular momentum will play an important role, since it's in that case a conserved quantity. So let's recall what angular momentum is and what its relevant properties are. Angular momentum is a measure of how much a particle is rotating around a chosen origin. If a particle has more speed or mass, it has more momentum, so it also has more angular momentum. Moreover, if a particle with a fixed speed moves in a larger circle, it has a larger angular momentum. If a particle is rotating around a chosen origin, the velocity vector must always be perpendicular to the coordinate vector. If the velocity vector is parallel to the coordinate vector, there is no rotation, so the angular momentum must be zero. These properties lead to the following expression for angular momentum. It is proportional to the particle's distance to the origin and its momentum. Moreover, it is proportional to the sign of the angle between the coordinate vector and the momentum vector, so that it is largest when the two are perpendicular and zero when the two are parallel. When we define angular momentum as a vector quantity, it is thus given by the cross product of position and momentum. To demonstrate that angular momentum is conserved if a central force is present, we calculate the time derivative of angular momentum. By applying the product rule, we find two terms. In the first term, we can write the time derivative of position as velocity and the momentum as mass times velocity. In the second term, we can write the time derivative of momentum as force. The first term vanishes because the velocity vector is parallel to itself, and the cross product of two parallel vectors vanishes. The second term vanishes by the assumption of a central force, which means that the coordinate vector and the force vector are parallel, which means that cross product vanishes. Now let's find the expression for the angular momentum of a particle that is moving in a straight line some distance away from the origin. First, we write the coordinate vector as a function of time. Then, we write down the momentum vector, which is constant in time. Taking the cross product of these two vectors gives the angular momentum vector. Lastly, we find an expression for the angular momentum of a particle that moves arbitrarily in the xy plane. We can write any position using polar coordinates, where the orientation of the x-axis is arbitrary. To calculate the momentum vector, we take the time derivative of the position vector. This time derivative can be calculated using the product rule. Now that we have expressions for both the position vector and the momentum vector, we can calculate the angular momentum vector by taking the cross product of the two. Note that the first term in the expression for the momentum vector is parallel to the position vector, so this term vanishes when taking the cross product. Taking the cross product with the remaining term yields a vector which can be simplified using the fact that cosine squared plus sine squared equals 1. With these results, we can now analyze Coulomb scattering. Suppose we have an incident charged particle with a certain impact parameter and a certain initial velocity. It will be scattered by the Coulomb force from another charged particle. We assume that this second particle is much more massive, so that it experiences negligible recoil. We know the initial angular momentum of the particle, since it is initially moving in a straight line. If we describe the trajectory of the particles in polar coordinates with respect to some axis, then we know that the angular momentum at any point along the trajectory will be equal to the initial angular momentum, because angular momentum is conserved when a central force is present. We can rewrite this expression to solve for 1 divided by the radius squared. The strength of the Coulomb force is proportional to 1 divided by the radius squared, so we can now write the force that the particle experiences in terms of the rate at which its angle changes. Now consider the fact that the incident particle has some momentum vector, and after scattering it has some other momentum vector. If no energy is transferred to the central charged particle, then the scattered particle has the same momentum before and after scattering. we can define the difference in the momentum vector, and this is the axis with respect to which we define the angle of the particle's position. When we define the scattering angle, we see from the geometry of an isosceles triangle how the magnitude of the difference factor depends on the scattering angle. Moreover, since force is the time derivative of momentum, the difference in momentum is given by integrating the force over time. Since we only care about the component of the force that points in the direction of the difference factor, we project the force vector onto that direction. We can rewrite the time integral as an integral over angle. When doing so, we must also change the limits of integration accordingly. From the geometry, we can find the angles at time minus infinity and time plus infinity. Then we can perform the integration straightforwardly. Note that we have now obtained a relation between the scattering angle and the impact parameter. We rewrite this equation to find an explicit expression for the impact parameter as function of the scattering angle. We can plug in the constant of the Coulomb force, and we can write sine over cosine as tangent. Recall that for a rotationally symmetric system, we found a formula for the differential scattering cross-section, which indicates the probability that a particle gets scattered to a certain solid angle, assuming a random impact parameter. Plugging in the expression we found, and simplifying, gives the scattering formula that Rutherford derived mathematically and Geiger and Marsden later verified experimentally. The scattering experiments confirmed Rutherford's idea that a lot of charge in an atom is confined to a compact nucleus, which results in a large Coulomb force and high scattering angles. The experimental results were furthermore used to derive an upper bound for the size of the atom's nucleus. In deriving the scattering formula, we assume that the alpha particle only experiences the Coulomb force, and that no energy is transferred to the nucleus. But we can expect deviations from the scattering formula if these assumptions are violated. For example, if the impact parameter is small compared to the nucleus, and the initial kinetic energy is large enough to overcome the Coulomb repulsion, then the alpha particle may come in direct contact with the nucleus, and thus experience different forces than just the Coulomb force. However, no such deviations from the scattering formula were observed experimentally. Therefore, it can be concluded that the alpha particle did not collide with the nucleus, even when it was shot directly at the nucleus. This means that the nucleus must be smaller than the distance of closest approach. If the alpha particle has some known initial velocity, then it has some known initial kinetic energy. At the distance of closest approach, the alpha particle has come to a standstill before it reverses direction. Therefore, all its kinetic energy has been converted to potential energy. So if we equate the potential energy to the initial kinetic energy, we can solve for the distance of closest approach, which gives an upper bound for the size of the nucleus. Plugging in the relevant values gave a size of the nucleus that turned out to be several orders of magnitude smaller than the size of the atom. Thus it appeared that atoms consist mostly of empty space. After Rutherford concluded that the atom has a small nucleus, where a lot of positive charge is concentrated, the next question is how the electrons are arranged in the atom. There is an attractive force between the negatively charged electron and the positively charged nucleus. So to explain why the electron doesn't crash into the nucleus, it was proposed that the electrons orbit the nucleus, just like the planets orbit the Sun. A planet can in principle orbit the Sun in many different ways. If the planet were nudged slightly, then its orbit would also change slightly. However, it was observed that all atoms of the same element have identical properties, so somehow all atoms should have the same electronic orbits, which cannot be perturbed the way planetary orbits can be perturbed. So, Niels Bohr proposed that for an atom of a certain element, the electron can occupy only certain specific orbits. This is contrary to our understanding of classical mechanics. Moreover, if we have an electric charge that has an electric field, then if we make the charge oscillate, it will emit electromagnetic radiation. This is, for example, how antennas work. So an orbiting electron should be emitting radiation, and as it loses energy via the radiation, its kinetic energy should decrease, which means the electron should spiral into the nucleus. Since this is not observed to happen, Bohr simply postulated that an orbiting electron does not radiate, contrary to what classical electrodynamics predicts. Rather, to explain atomic spectral lines, Bohr stated that when an electron jumps from a high-energy orbit to a low-energy orbit, radiation is emitted, and the frequency of the emitted radiation is given by the energy difference divided by Planck's constant, which is basically Einstein's formula for photon energy. However, from classical electrodynamics, it is known that if an electron is oscillating with a certain frequency, the emitted radiation should have the same frequency. This is, for example, what we assumed in Lorentz's explanation for the Zeeman effect. But in Bohr's model, the frequency of the emitted radiation appears unrelated to the frequency with which the electron orbits the nucleus. So Bohr's model contradicts well-established classical physics in several ways. Nevertheless, Bohr still proposed this model of the atom because it explains quite a few observations in an elegant way. First, it explains the spectral lines of hydrogen. An empirical formula that describes the spectral lines had been derived already, but it lacked any physical foundation, and it involved an arbitrary physical constant called the Rydberg constant. With Bohr's model, one can explain the positions of the spectral lines, and one can derive the Rydberg constant from more fundamental physical constants such as Planck's constant and the electron charge. Moreover, with the Bohr model, one can calculate the radius of the electron orbits, which indicate the size of the atom. It can be verified that this calculated size corresponds well to the measured size of an atom. Lastly, from the energy levels of Bohr's electron orbits, one can calculate the ionization energy, which is the energy required to knock an electron out of the atom. This calculated ionization energy also corresponds well with the measured value. Moreover, the predictions of the Bohr model were confirmed in the Frank-Hertz experiment. So Bohr's model contradicts the well-established classical physics, but it also provides convincing explanations for otherwise unexplained observations. How can we resolve this contradiction? According to Bohr's correspondence principle, his quantum mechanical rules should reduce to the rules of classical physics in limiting cases. For example, if an electron is in a high-energy orbit and drops to the energy level below it, then the frequency of the emitted radiation equals the frequency of the electron's orbit, as is expected from classical electrodynamics. Note that Bohr proposed the quantization of atomic energy levels, but he still rejected Einstein's proposal of quantized electromagnetic radiation. Now let's look in more detail at the electron orbits and the energy levels that Bohr assigned to them. If an electron rotates in circles with a certain angular frequency, then its position can be described as a function of time as cosine omega t sine omega t. We find the velocity vector by taking the time derivative of the position vector, and we see that the velocity vector is perpendicular to the position vector. We can take another time derivative to find the acceleration vector. This acceleration must be due to a force, which is in our case the Coulomb force between the positively charged nucleus and the negatively charged electrons. So we can calculate the magnitude of the acceleration and equate this to the magnitude of the Coulomb force. From this expression, we can write the angular frequency in terms of the radius of the orbit, or we can write the radius in terms of the angular frequency. Now let's calculate the angular momentum of the orbiting electron, which is given by the cross product of the position vector and the momentum vector. By plugging in the expressions for the position vector and velocity vector, we find an expression for the angular momentum in terms of the electron's angular frequency and the radius of the electron orbit. Using the expressions we found earlier, we can either eliminate the angular frequency and express the radius in terms of angular momentum, or we can eliminate the radius and write the angular frequency in terms of angular momentum. Next, we calculate the energy of the orbiting electron, The electron's potential energy follows directly from the definition of the Coulomb force. Using the equation between the centripetal force and the Coulomb force, we can express the potential energy in terms of the electron's angular frequency and the radius of its orbit. The kinetic energy is given by 1/2 mv squared, which we can rewrite using the expression for the velocity. The total energy of the electron is given by its potential energy plus its kinetic energy. By eliminating the angular frequency, we can write the total energy in terms of only the orbit's radius. Then we write the radius in terms of angular momentum. Bohr then imposed the condition that the electron's angular momentum can only be integer multiples of the reduced Planck's constant, which is Planck's constant divided by 2π. This defines the quantized energy levels of the electron. Now we relate the electron's energy levels to the empirical formula for the spectral lines of hydrogen. To find the wavelengths of the spectral lines, we multiply the empirically determined Rydberg constant with the difference of the reciprocals of squared integers. We can relate wavelength to frequency and frequency to energy via Einstein's relation. If we take for the energy the difference between the quantized electron energy levels, and we fill in the relevant values for the hydrogen atom, we then find a theoretical expression for the empirically determined Rydberg constant. A good match between the theoretical and experimental value was found. Now let's see how the quantum rules reduce to the classical rules in limiting cases, as required by Bohr's correspondence principle. Consider the energy difference between two subsequent energy levels. For high energy levels, this difference can be well approximated by differentiating the energy with respect to the number of the energy level. We can calculate this derivative and substitute the electron's angular momentum. If we then rewrite the energy difference in terms of the electron's angular frequency, we recover Einstein's relation, but now for the electron's frequency instead of the radiation's frequency. Therefore, we see that in this limit the electron's frequency coincides with the radiation's frequency, as predicted by classical electrodynamics. Now let's see what the Bohr model can tell us about the size of an atom. We have expressed the radius of the electron's orbit in terms of angular momentum, and we have specified what values the angular momentum can take. Therefore, we can calculate the radius of the smallest electron orbit and take this as an indication for the size of the atom. This radius is called the Bohr radius, and it has the same order of magnitude as the experimentally measured size of the atom. To calculate the ionization energy of a hydrogen atom, we calculate its lowest energy. This also yields a value that matches well with experiment. Another convincing experimental demonstration of quantized atomic energy levels is the Frank-Hertz experiment. In this experiment, electrons are accelerated with a certain potential. The electrons can travel through the positively charged grid, and the collection plate behind it has a slight negative charge compared to the grid, so that only fast-moving electrons can reach it and form a measurable current. The space in between is filled with mercury vapor. As the accelerating voltage is increased, the measured current increases as well, as expected. But once the voltage reaches 4.9 volts, there is a sudden drop in the measured current. This implies that electrons can only lose energy to the mercury atoms if the electron energy exceeds 4.9 electron volts. If the voltage is increased further, then electrons that lost their energy are re-accelerated, so the current increases again. But when the voltage reaches twice 4.9 volts, there is again a drop in the measured current, which means that the re-accelerated electrons lost their energy again to the mercury atoms. This pattern repeats many times. This observation can be explained by assuming that there is an energy difference of 4.9 electron volts between different electron orbits. An incident electron can only lose its energy when it's sufficient to knock an electron from a lower orbit to a higher orbit. Moreover, light with a wavelength of 254 nanometers was emitted by the mercury vapor. This can be explained by the excited electron dropping back from the higher orbit to the lower orbit. According to Einstein's relation, the light that is emitted should indeed have a wavelength of 254 nanometers. These observations are convincing evidence for quantized energy levels in the mercury atom. Further evidence for the Bohr model came with the explanation of the Pickering series. For some stars, it was observed that the positions of the spectral lines were not given by the difference of reciprocals of squared integers, but rather by half integers. According to Bohr's formula, this can be explained by assuming that the spectral lines are not due to hydrogen, whose nucleus only has 1 time the electron charge, but rather are due to ionized helium, whose nucleus has twice the electron charge. As a result, we would have for ionized helium 4 times the Rydberg constant for hydrogen. However, Alfred Fowler was initially not convinced by this explanation, pointing out that experimentally, it was measured that the ratio with the Rydberg constant was not exactly 4, but 4 plus a little bit. Bohr responded to this that in his theoretical calculation he made an approximation that leads to this discrepancy. In the calculation, we assumed that the electron is attracted by the nucleus, but we ignored the fact that the nucleus is also attracted by the electron. This approximation is justified because the mass of the nucleus is much greater than that of the electron, so the nucleus is barely moved by the force. However, if we want a more accurate result, we need to take into account that the mass of the nucleus is in fact finite, and that it is therefore affected by the Coulomb force from the electron. To calculate the impact of this effect, we first note that by Newton's third law, the forces are equal and opposite. By Newton's second law, the force is equal to the mass times acceleration. Since we're interested in the relative motion between the electron and the nucleus, we take the difference of the accelerations. We rewrite the acceleration of the nucleus in terms of the acceleration of the electron. We write the electron's acceleration as the force divided by the mass, and we impose that the relative acceleration is equal to the force divided by some effective mass, called the reduced mass. From this follows the expression for the reduced mass, which we have to use instead of the electron mass. First, let's calculate the reduced mass for hydrogen. We use the definition of the reduced mass and write it in terms of the mass ratio between the proton and electron, which were well known from experiments. We do the same for ionized helium, whose nucleus is 4 times heavier than that of hydrogen. With the resulting expressions, we can find the ratio between the Rydberg constants for hydrogen and helium. The ratio is determined by the ratio of the squared nuclear charges and the reduced masses. By plugging in the expressions we found, we obtain a value that matches well with the experimental value. So Bohr's model of the atom explains certain phenomena with convincing accuracy and elegance. However, there were still some observations that Bohr's model did not explain, which means the model had to be extended. One such observation is the Stark effect. Just like in the Zeeman effect, spectral lines were split by a magnetic field, in the Stark effect, the lines are split by an electric field. To explain this effect, Arnold, Sommerfeld, and others replaced Bohr's quantization condition with a more general quantization condition. This condition works with the generalized coordinate q and the generalized momentum p, as known from Hamiltonian mechanics. It says that if we integrate the generalized momentum over one period of the particle's motion, we should obtain an integer multiple of Planck's constant. If we assume circular motion with a certain radius and angular frequency, we see that we obtain Bohr's quantization condition. However, in addition to circular orbits, Sommerfeld's quantization also defines a set of quantized elliptical orbits. These orbits are different, but they all have the same energy. Different states having the same energy are said to be degenerate. When an electric field is applied, the different orbits are affected differently, which causes them to have different energies. Thus, the degeneracy is lifted and the spectral lines are split, as is observed in the Stark effect. We can also apply this new quantization condition to the harmonic oscillator. The position oscillates with a certain amplitude and angular frequency. The momentum is found by taking the time derivative. To calculate the integral that is quantized, we rewrite it as an integral over time. The period of one oscillation is given by 2 pi over the angular frequency. We can write down the integral and calculate it straightforwardly. As prescribed by the quantization condition, we set it equal to an integer multiple of Planck's constant. The total energy of the harmonic oscillator can be determined by the maximal momentum of the particle. Using the expression found from the quantization, we find that the energy of the harmonic oscillator is quantized in integer multiples of Planck's constant times the oscillation frequency. This is what Planck had used in the derivation of his radiation law, and what Einstein had used to explain the heat capacities of solids at low temperature. Furthermore, Sommerfeld extended his model by taking into account relativistic effects to explain the finer features of the spectral lines of hydrogen. So the quantization of molecular and atomic vibrations was accepted as an explanation for the heat capacities of solids, and the quantization of atomic energy levels was accepted as an explanation for atomic spectral lines. However, Einstein's original proposal of quantized electromagnetic radiation was still not accepted at this time, so he continued to work out arguments for this idea. The guiding principle is that by assuming certain quantum processes, one should be able to derive Planck's radiation law. The law for blackbody radiation has been considered in various ways, which are worth summarizing. In the first attempt of deriving the law for blackbody radiation, Wilhelm Wien assumed that the radiation distribution is closely related to the velocity distribution of molecules. This makes some sense because it is known that the motion of charged particles generates electromagnetic radiation. Later, Max Planck tried to derive the radiation distribution using principles of entropy as a starting point. This is because Planck was trying to figure out whether electromagnetism could explain the irreversibility of processes. When an experimental mismatch with Wien's radiation law was found, Planck tweaked his derivation of Wien's radiation law so that it now fits the data. To find a theoretical justification for his tweaking, he turned to Boltzmann's statistical mechanics. Planck had to assume that energy came in discrete packets, but he saw this more as a mathematical tool rather than a physical reality. Albert Einstein, however, drew the conclusion that radiation must be quantized. As we will see in the following, Einstein tried to derive Planck's radiation law by assuming that light quanta are absorbed and emitted by molecules or atoms at certain rates, and that these processes are in equilibrium when Planck's law is satisfied. Moreover, Einstein revived Wien's original idea that the radiation distribution must be related to the molecule's velocity distribution. Einstein demonstrated that if photons transfer momentum to the molecules during emission and absorption, and Planck's radiation law is satisfied, then the velocities of the molecules are distributed as prescribed by the equipartition theorem. First, let's see how Planck's radiation law can be derived by requiring equilibrium between absorption and emission processes. We assume that a molecule can be in one of two states: the ground state with some energy E1, or the excited state with energy E2. We consider a system with a bunch of molecules that can be in either state. According to Boltzmann's statistical mechanics, the probability that a molecule is in a state with a certain energy is proportional to the density of states times the Boltzmann factor. Now Einstein supposed that there is also radiation present in the system, and the molecules can interact with the radiation via three different processes. The first is spontaneous emission, where a molecule transitions from the excited state 2 to the ground state 1. In doing so, a photon is emitted. The rate at which this happens is given by the coefficient A21. To justify the assumption that such a process exists, Einstein points out that this is what appears to happen in radioactive processes where gamma rays are emitted. The second process is absorption. A molecule starts in the ground state 1 and absorbs a photon to transition to the excited state 2. The rate at which this happens is given by the coefficient B12. Lastly, Einstein assumed the process of stimulated emission. A molecule starts in the excited state 2, and through interaction with an incident photon transitions to the ground state 1, while emitting a photon in addition to the incident photon. The rate at which this happens is given by the coefficient b21. The idea is that molecules are continuously transitioning between states through the interaction with the radiation field. In an equilibrium situation, the radiation field is such that the number of molecules that are in a given state remains constant over time. Let's consider the rate at which the number of molecules in state 1 changes. First, note that there are two processes which increase the number of molecules in state 1. The rate at which these processes occur depends on how many molecules there are in state 2. The rate at which spontaneous emission occurs is proportional to the coefficient A21. The rate at which stimulated emission occurs is proportional to the coefficient B21. But since this process requires incident radiation, its rate is also proportional to the radiation energy density. The rate at which the number of molecules in state 1 decreases is proportional to the number of molecules in state 1. The rate at which absorption occurs is proportional to the coefficient B12 and the radiation energy density. So we now know at which rate the number of molecules in state 1 changes, and we know that in equilibrium this rate of change must be 0. This yields an equation which can be solved for the radiation density. We can substitute the expressions for the probability that a molecule is in state 1 or state 2. This equation resembles Planck's radiation law, assuming certain values for the ratios of coefficients. Moreover, the Bohr model of the atom states that the difference between energy levels equals Planck's constant times the radiation frequency. So we see that the form of Planck's radiation law can be derived by assuming quantum processes of spontaneous emission, absorption, and stimulated emission. Stimulated emission would later be used in the laser, which itself stands for light amplification by stimulated emission of radiation. The next thing that Einstein did was to demonstrate how the radiation distribution determines the velocity distribution of the molecules, by assuming that photons transfer momentum during emission and absorption. The radiation interacts with the molecule's motion as follows. Firstly, as photons randomly transfer momentum to a molecule, it starts moving around randomly. Secondly, if a molecule is moving in a certain direction, the photon collisions act as a force of friction, which slows down the molecule. One might remark that in an equilibrium state, the radiation distribution is isotropic, so it cannot push a molecule harder on one side than another. But one must realize that the molecule is moving, and in the molecule's moving frame of reference, the radiation distribution becomes non-isotropic. As a result, the radiation exerts a net force on the molecule opposing its motion, thereby acting as a force of friction. So the fluctuations in the molecular motion and the dissipation of that same motion are related because they are of the same origin, namely the many random collisions with photons. This relation is described in what is now known as the fluctuation dissipation theorem. Einstein had already used a very similar analysis to explain Brownian motion. Just like the random motion of dust particles can be explained by many random collisions with air molecules, the random motion of molecules can be explained by many random collisions with photons. So to demonstrate the relation between the radiation distribution and the molecular velocity distribution, we proceed as follows. First, we calculate how the momentum of a moving molecule is dissipated due to the radiation as seen from its moving reference frame. Then, we calculate how the molecule's momentum will fluctuate due to the random photon interactions. With these two results, we can calculate the average kinetic energy of the molecules. We will see that this equals kBt over 2, as required by the equipartition theorem. This match with well-established theory is evidence for the hypothesis that photons carry momentum and transfer it during absorption and emission processes. So first, let's see how radiation is transformed when going from a static frame of reference to a moving frame of reference. Consider a plane wave with some wavelength lambda at some angle theta with the x-axis. This wave is seen by a molecule that moves with a velocity v in the x direction. To find what this wave looks like in the molecule's frame of reference, we need to apply a Lorentz transformation, as prescribed by special relativity. We will see that as a consequence of this transformation, the wavelength and frequency change, the angle with the x-axis changes, and the intensity of the wave changes. To demonstrate this, consider the expression for the plane wave in the static frame of reference. We apply the Lorentz transformation to move to the molecule's frame of reference. Then we collect all the terms with the position x' and the terms with the time t'. We simplify the expression by using the fact that the angular frequency omega divided by the wave number k equals the speed of light c. The resulting expression corresponds to some plane wave with a wave number k', angle theta', and angular frequency omega'. By comparing expressions, we find how the angular frequency in the molecule's frame of reference relates to the original angular frequency. Moreover, we see how the wave number is transformed between reference frames. In every reference frame, the speed of light is the same, so the wave number k' equals the angular frequency omega' divided by the speed of light c. We thus find how the angle of the plane wave in the molecule's reference frame relates to the angle in the static reference frame. This expression can be simplified by plugging in the expression for the transformed angular frequency that we found earlier. So we have found how the frequency of the wave changes when moving to the molecule's frame of reference and how the direction of the wave changes. Now let's see how the intensity changes when switching between reference frames. An electromagnetic plane wave consists of an oscillating electric field and magnetic field. These fields are perpendicular to each other and perpendicular to the propagation direction. We can write down the expressions for the electric and magnetic fields and then transform them according to the Lorentz transformation, as derived in a previous video on special relativity. We can apply this transformation to the fields and calculate the intensity, which is proportional to the square of the field, in the molecule's frame of reference. We have now found how the frequency, direction, and intensity of radiation changes when moving to the molecule's frame of reference. If we assume that the molecule's velocity is much smaller than the velocity of light, we can simplify the expressions by linearizing them. With these results, we can now calculate how the radiation energy density transforms when moving from the static reference frame to the molecule's reference frame. Note that in the static reference frame, the radiation energy density is independent of the angle if it is in equilibrium. Since the radiation energy density defines the radiation energy per unit frequency per solid angle, we must multiply it with the frequency interval and solid angle interval to relate it to the intensity. Combining these results tells us how the radiation energy density in the molecule's reference frame is related to the radiation energy density in the static reference frame. Now let's work out this expression further by using the other results we found. First, we invert the relation between the original frequency and the transformed frequency, and linearize for small values of v over c. We can straightforwardly calculate the derivative. To find the derivative for the solid angle, we write the differential solid angle in terms of the polar angle and azimuthal angle, and note that we can write it as the differential of the cosine of the polar angle. Therefore, we can write the derivative of the solid angle as the derivative of the cosine of the polar angle. So we invert the relation between the original angle and the transformed angle, linearize for small values of v over c, and calculate the derivative. The radiation energy density in the static reference frame is evaluated at the frequency in the static reference frame. But eventually we want an expression in terms of the frequency in the molecule's reference frame. Assuming the shift in frequency is small, we can Taylor expand the expression for the radiation energy density. We can plug in the frequency shift that we calculated. Combining all these results and linearizing for small values of v over c, we find an expression for the radiation energy density. This radiation distribution that is seen by the molecule determines at which rate the molecule experiences photon absorption and stimulated emission. To calculate these rates, we first define the normalization constant, which guarantees that the probabilities found from the Boltzmann factors add up to 1. The rate at which photons are absorbed is given by the coefficient B12 times the probability that the molecule is in state 1 times the radiation energy density. The rate at which stimulated emission occurs is given by the coefficient B21 times the probability that the molecule is in state 2 times the radiation energy density. When we derived Planck's law by requiring an equilibrium between absorption and emission processes, we found that B21 times the density of states for energy level 2 equals B12 times the density of states for energy level 1. To find out how much momentum is transferred from the radiation to the molecule, we assume that each photon carries a momentum equal to the photon energy divided by the speed of light, as known from special relativity. If we only consider the x component of the momentum, we have to include the cosine of the angle with the x-axis. Depending on whether a photon is absorbed or emitted, the transferred momentum is positive or negative. To find the total rate at which x momentum is transferred, we have to average over all solid angles at which a photon can be absorbed or emitted. The photons that are absorbed give a contribution with a positive sign, and the photons that are emitted give a contribution with a negative sign. Now we calculate the integral over all solid angles, which can be expressed as an integral over the azimuthal angle and the polar angle. First, consider the terms in the integrand that contain a product of cosine and sine. That integral reduces to 0. The same goes for terms containing cosine to the third times sine. There are two terms containing cosine squared times sine. This integral has a non-zero value of 4 pi over 3. Plugging in these results gives a final expression for the rate at which momentum in the x direction is transferred from the photons to the molecule. We can write this rate of momentum transfer as some constant times the velocity of the molecule. This equation says that the faster the molecule moves, the stronger is the radiation force that opposes this motion. From the quantum hypothesis, we know that the difference in energy levels equals Planck's constant times the radiation frequency. This yields an expression for the constant that describes dissipation due to the photon interactions. Because the photon interactions occur randomly, there will be fluctuations in the molecule's momentum. Let's calculate how large these fluctuations are. We saw that per photon interaction, the momentum that is transferred in the x direction is given by the photon energy divided by the speed of light times the cosine of the angle with the x-axis. To find the average of the square of the transferred momentum, we take the average over all solid angles. We can write the differential solid angle in terms of the polar angle and azimuthal angle. This integral can be calculated straightforwardly. Momentum is transferred during either photon absorption or emission, and the rates of these two processes are equal in case of equilibrium. If we define the normalization constant of the Boltzmann factors, we can calculate the number of photon emissions and absorptions that occur in a certain time interval. Knowing that the rate of emissions equals the rate of absorptions, we can write the total number of photon interactions as twice the number of photon absorptions. To find the average squared momentum that is transferred per unit time, we multiply the average squared momentum that is transferred in a single photon interaction with the number of photon interactions per unit time. Now we're going to combine the calculation results for dissipation and fluctuations to find the average kinetic energy of the molecule due to motion in the x direction. During a small time interval, momentum will be transferred because a moving molecule sees an asymmetric radiation distribution, and there will be some random fluctuations because the photon interactions are random. If the system is in equilibrium, then the velocity distribution of the molecules is constant in time. Therefore, taking the expectation value of the squared momentum after the momentum transfer should be the same as before the momentum transfer. We can write out the square and cancel out several terms. Because we consider a small time interval, the square of that time interval is negligible. The expectation value of the transferred momentum due to the random directions of photon interactions vanishes due to symmetry, because the asymmetric effects due to the molecule's velocity have been accounted for separately. The terms mv² cancel out on both sides. Only two terms remain. These can be rewritten so that we obtain the expectation value for the molecule's kinetic energy due to motion in the x direction. This expression can be worked out further by plugging in the results we found for the dissipation and the fluctuation of the molecule's motion. Several factors that are common to both the numerator and the denominator can be cancelled out. The resulting expression contains the radiation distribution, for which we plug in Planck's radiation formula. We also need to plug in its derivative with respect to frequency. Let's focus only on the term where the radiation distribution and its derivative occur. We plug in the radiation formula and its derivative. We add the two fractions using a common denominator. We recognize one factor as being the radiation distribution. We plug this result in the expression for the average kinetic energy. Cancelling out factors in the numerator and denominator yields the final result. The molecule's average kinetic energy due to motion in the x direction is 1/2 times Boltzmann's constant times the temperature. This is consistent with the equipartition theorem. To Einstein, the result that molecular kinetics can be related to the radiation distribution by assuming that photons transfer momentum during random emissions and absorptions made a quantum theory of radiation almost unavoidable. At the same time, however, he admitted that it's still unclear how the quantized nature of light should be reconciled with its well-established wave nature. In spite of Einstein's arguments, widespread acceptance of the idea of quantized radiation only came after the discovery and explanation of Compton scattering. Compton scattering describes how X-rays are scattered by electrons. This scattering gives insight into the nature of X-rays. By the time Compton scattering was discovered, there had already been lengthy disputes about the nature of X-rays. So to understand the context of the discovery of Compton scattering, let's first give a brief history of research in X-rays. Experiments with the Crookes tube led to the study of cathode rays, which turned out to be negatively charged electrons, canal rays, which are positively charged ions, and X-rays, discovered by Wilhelm Röntgen. When these rays were discovered, discussions arose on the nature of these rays. Do they consist of particles, or are they electromagnetic waves like light? Meanwhile, the discovery of radioactivity also led to the study of different types of rays. 3 different kinds of rays were identified, and they were named alpha, beta, and gamma rays. These rays are distinguished by their ability to penetrate different materials, and by the way they are deflected in a magnetic field. Marie Curie correctly observed that alpha rays are of the same nature as canal rays, beta rays are like cathode rays, and gamma rays are like X-rays. Regarding the nature of X-rays, it was discovered that X-rays form a diffraction pattern when scattered by a crystal. This was convincing evidence that X-rays are electromagnetic waves, with a very short wavelength that is comparable to the distance between atoms in a crystal. However, there were also indications that X-rays have a particle-like nature. For example, if an electron with a certain initial kinetic energy generates X-rays, then those X-rays can give a second electron the same kinetic energy that the first electron initially had. But this is not what you'd expect if X-rays were waves, because a wave would spread out and transfer only a portion of the initial energy. For example, if you drop a rock from a certain height in the water to create water waves, then those waves cannot raise another rock to the original height of the first rock. The scattering experiments of Arthur Compton quantitatively demonstrated that the scattering of X-rays by electrons can be understood by assuming that X-rays consist of particles, which is consistent with Einstein's light quantum hypothesis. To understand how Compton performed his scattering experiment, let's first consider how X-rays are generated. In an X-ray tube, electrons are accelerated from the cathode to the anode, which is made of molybdenum. When the electrons collide with the anode, X-rays are generated by 2 different processes. The first process produces what is called Bremsstrahlung, which translates to braking radiation. If an electron with high velocity reaches the anode, it can suddenly get blocked or deflected by the atoms there. Such a sudden change in velocity is an acceleration, and we know that accelerating charges generate radiation. Since the electrons can undergo a broad range of accelerations, the resulting X-ray radiation has a broad spectrum. The second type of X-rays that are formed are characteristic X-rays. These are X-rays with wavelengths that depend on the material of which the anode is made. The atoms of the anode have certain energy levels, as proposed by the Bohr model. These levels are labeled K, L, M, etc. An incident electron can knock an electron from a low energy level to a higher energy level. When the electron drops back to the lower level, it emits radiation with a frequency that depends on the difference between energy levels, which depends on what element the anode consists of. The radiation due to an electron falling from the L shell to the K shell is called the K-alpha line in the radiation spectrum. Radiation due to an electron falling from the M shell to the K shell is called the K-beta line. Next, we must understand how Compton experimentally measured an X-ray spectrum. It was done using a method called Bragg spectrometry. In this method, we have a crystal which has a certain distance d between the atoms. If we shine radiation with a certain wavelength lambda on it, at a certain glancing angle theta, then we can calculate the path length difference between the light reflected from the two different layers. The reflected light interferes constructively when the path length difference is an integer multiple of the wavelength. Therefore, if we fix the glancing angle of the incident light, only a certain wavelength is reflected. So if we shine light consisting of multiple wavelengths onto the crystal, then by rotating the crystal, we can select separate wavelengths, and thereby measure the spectrum of the incident light. Now let's look at the experiment that Arthur Compton performed. An X-ray tube with a molybdenum anode was used to generate X-ray radiation. The rays are collimated by two slits. The spectrum of the transmitted light is analyzed with a calcite crystal that acts as a Bragg spectrometer. The resulting spectrum is compared to the spectrum of the X-rays that are scattered by 90 degrees from graphite. It turns out that when the X-rays are scattered by the graphite, the wavelength of the rays is increased. This shift in wavelength is contrary to what classical electrodynamics can explain. According to classical electrodynamics, if radiation of a certain frequency hits an electron, then that electron starts oscillating with the same frequency. The electric field lines of that electron also oscillate with the same frequency, so the frequency of the scattered radiation is the same as the frequency of the incident radiation. Therefore, the wavelengths of the scattered and incident radiation must also be the same. So to explain the observed wavelength shift in the scattered X-rays, we must look for an explanation outside of classical electrodynamics. Compton's explanation of the observed wavelength shift is the following. We assume that the incident radiation consists of photons, and each photon has a momentum that is equal to Planck's constant times the radiation's frequency divided by the speed of light. This is the same assumption that Einstein made in his light quantum hypothesis. When this incident photon hits an electron, the electron will be set in motion with a certain velocity v. In special relativity, it is common to write the velocity as beta, a fraction of the speed of light. The relativistic momentum is given by gamma times the electron mass times the electron's velocity. This can be written as a function of beta. The photon is scattered at a certain angle. It will have a certain momentum that defines the frequency of the scattered radiation. In this interaction, total momentum is conserved. That is, if we add the momentum vector of the scattered photon to the momentum vector of the scattered electron, we obtain the momentum vector of the incident photon. According to the law of cosines, the squared length of the side opposite to the angle theta is equal to the sum of the squared lengths of the other sides minus twice the product of those lengths times the cosine of theta. Moreover, during the interaction, conservation of energy should hold. The total energy before the collision is equal to the energy of the incident photon, Planck's constant times the radiation's frequency. After the collision, the energy is divided over the scattered photon and the kinetic energy of the electron, which is equal to the total relativistic energy minus the rest mass energy. We can write gamma in terms of beta. Using these equations for momentum conservation and energy conservation, we can solve for the frequency of the scattered light. First, we use the equation for energy conservation to solve for beta squared. Then, we plug this expression into the equation for momentum conservation. We substitute beta squared, work out the product, and then expand the square, and again expand the product. We equate this left-hand side of the momentum conservation equation to the right-hand side. We expand the square and cancel terms that are on both sides of the equation. We can now solve for the frequency of the scattered photon. This equation relates the scattered frequency to the incident frequency. We can find the wavelength of the scattered light from its frequency. We expand the product and find the scattered wavelength in terms of the incident wavelength. We see that the wavelength shift is independent of the incident wavelength, but varies with the scattering angle. For long incident wavelengths, this wavelength shift may be unnoticeably small, but for X-rays with short wavelengths, such a wavelength shift can become significant. To further verify this result, Compton later performed additional measurements where the scattering angle is varied. Indeed, the observed wavelength shift as a function of scattering angle matches the theory. In spite of this convincing evidence for the existence of light quanta, it was still not clear how it would be reconciled with the wave nature of light that is clearly evidenced by interference effects. Nonetheless, Einstein as well noted that the results of Compton's experiments are strong evidence for the quantization of radiation. Louis de Broglie noted that, by now, the experimental data conclusively indicates that light is indeed quantized, as Einstein anticipated almost 20 years earlier. Einstein's explanation of the photoelectric effect, Compton's explanation of the wavelength shift of scattered X-rays, Bohr's model of quantum jumps between atomic energy levels, and Einstein's explanation of energy fluctuations due to random photon interactions, they all point to the reality of light quanta. However, it has remained unclear how this could be reconciled with the well-established wave nature of light. De Broglie attempted to resolve this contradiction. His proposal was that all particles, whether they be particles of light or electrons, are accompanied by some non-material phase wave. This wave obeys wave mechanics, so it can diffract and interfere, and it determines the trajectories along which particles move. Therefore, light can exhibit both particle-like behavior and wave-like behavior. When light is incident on some atom, the phase wave determines the probability that some interaction takes place. Moreover, by assuming that electrons are also accompanied by some phase wave, de Broglie was able to derive the quantization condition that Bohr used for his energy levels in his atomic model. Now let's examine the reasoning behind this phase wave in more detail. According to relativity, a particle with a certain mass has a certain energy. According to the quantum hypothesis, a certain amount of energy corresponds to a certain frequency. Putting these two equations together implies that particles with a certain mass have a certain frequency associated to them. The fact that the particle has some frequency suggests that the particle should have some sort of wave nature. A wave nature would explain why particle states can be quantized. It is known from classical physics that a wave that is subject to boundary conditions can oscillate only in certain modes. For example, a guitar string that is clamped at two ends can only form standing waves with certain wavelengths. A standing wave can be written as a left-moving wave plus a right-moving wave. So if a particle is vibrating to the left and right, and to this particle is associated some sort of wave, then it stands to reason that the particle can only vibrate in discrete modes. This is consistent with Einstein's explanation for heat capacities at low temperatures, where he assumed that the energy of molecular vibrations is quantized. Similarly, when an electron orbits the nucleus of an atom, one may for the same reason expect quantized energy levels, which is consistent with Bohr's model of the atom. So let's see what this particle's wave function would look like. We can write the equation for energy quanta in terms of angular frequency and the reduced Planck's constant. The angular frequency of the matter wave can be expressed using the reduced Planck's constant. It is natural to suppose that the matter wave of a stationary particle is given by the cosine of the angular frequency times time, and we can plug in the expression we found for the angular frequency. What would the matter wave look like if the particle is moving with some velocity v? To find the answer, we observe the stationary particle from a reference frame that moves with velocity v. We thus find the new wave function by applying the Lorentz transform. We collect the term with position x and the term with the time t. We can recognize the expressions of the relativistic momentum and the relativistic energy. For a plane wave with some wave number k and angular frequency omega, the phase velocity is given by the angular frequency divided by the wave number. When we plug in the values we find that the phase velocity is not equal to the particle's velocity v. But if the particle's velocity is not equal to the phase velocity of its wave function, then how does the wave function relate to its particle's velocity? Suppose the wave function does not consist of just a single energy and momentum, but rather there is a slight spread in energy and a corresponding spread in momentum. We can rewrite the sum of two cosines as a product of two cosines. The propagation speed of the first factor is the same as the phase velocity we found before. The propagation speed of the second factor is called the group velocity, and it is given by the spread in the angular frequency divided by the corresponding spread in the wave number. This can basically be interpreted as the derivative of energy with respect to momentum. Using the relativistic energy-momentum relation, we take the derivative of both sides with respect to momentum and then solve for the derivative of energy with respect to momentum. Plugging in the relativistic definitions for momentum and energy, we find that the group velocity is equal to the particle's velocity. Therefore, we find that to find the particle's velocity from its wave function, we need to look at its group velocity. Note that if we use the non-relativistic energy-momentum relation, we can also calculate the derivative of energy with respect to momentum and find that the group velocity is equal to the particle's velocity. A somewhat more general derivation of the velocity of a wave packet is the following. Consider a wave function that is the sum of plane waves with different wavelengths and different phase velocities. This wave function will have a certain envelope which moves at a certain velocity, which is the group velocity that we're trying to find. The envelope is located at the position where all the terms in the summation are in phase with each other, so that they add constructively. Therefore, to find the position of the envelope, we require that the derivative of the phase with respect to the wave number equals 0. We can calculate this derivative and see that the position x of the envelope moves as a function of time t with a velocity that is equal to the derivative of the angular frequency with respect to the wave number. In the wave function, as proposed by Broglie, we see that the angular frequency is related to the particle's energy, as was required by Einstein's quantum hypothesis. We also see that the wave number is related to the particle's momentum. Therefore, the particle's momentum defines its wavelength, which is called the de Broglie wavelength. Moreover, we found that the particle's velocity is given by the group velocity of a wave packet. But we saw that to define a wave packet, we need a finite spread in wave numbers. Therefore, if the particle's wave function is to be localized, it cannot have a definite momentum. This hints at what would later become known as the uncertainty principle. Now let's see how de Broglie's matter wave hypothesis can be used to explain Bohr's quantization condition for the energy levels of the atom. When an electron orbits the nucleus at a certain radius, with a certain momentum, then the angular momentum can be calculated using the cross product. Bohr's quantization rule states that this angular momentum must equal an integer multiple of the reduced Planck's constant. Since for circular motion the momentum vector is always perpendicular to the coordinate vector, the cross product can be reduced to a regular product. The momentum can be rewritten using the de Broglie wavelength. By writing the reduced Planck's constant in terms of the regular Planck's constant, we find that the circumference of the orbit must equal an integer multiple of the wavelength. In other words, an electron can only orbit the nucleus if its wave function interferes constructively with itself. We saw that Bohr's quantization rule is a special case of Sommerfeld's more general quantization rule, which says that the momentum integrated over one period of motion should equal an integer multiple of Planck's constant. During the periodic motion, the momentum may change. For example, in a harmonic oscillator, the particle has a larger momentum in the center than at the sides. According to the expression for the de Broglie wavelength, it thus means that the wavelength also changes during the oscillation. If the particle has at some position a certain wavelength lambda and propagates by a small distance dx, then the phase shift it undergoes equals 2 pi over lambda times dx. If we plug these results in the quantization condition, we find that integrating the phase over one period must equal an integer multiple of 2 pi. Therefore, Sommerfeld's quantization condition can be interpreted as a condition for constructive interference. As the particle goes through the periodic motion, it must constructively interfere with itself. So the de Broglie wavelength elegantly explains the quantization conditions that we previously simply had to assume. But on top of that, there is also more direct experimental evidence for the de Broglie wavelength. One example is the Davison-Germer experiment. First, recall that for normal visible light, a diffraction pattern is larger for longer wavelengths and smaller for shorter wavelengths. When electrons are fired at a crystal, a diffraction pattern can be observed, which already demonstrates that electrons have a wave nature. Moreover, we can change the electron momentum by changing the accelerating voltage, which according to de Broglie should change the electron wavelength. Indeed, if the accelerating voltage is increased, the diffraction pattern shrinks, which indicates that the electron wavelength has been reduced. Moreover, G.P. Thomson, son of J.J. Thomson who had previously discovered the electron particle, also performed experiments that demonstrate the wave nature of electrons. In his experiment, he observed that electrons can form a diffraction pattern that is very similar to an X-ray diffraction pattern. Planck's radiation law started and guided many developments in quantum mechanics. However, by 1924, Planck's radiation law had not yet been derived using purely quantum mechanical principles. It had always been derived using a mixture of classical physics and some quantum mechanical assumptions. For example, Planck originally derived the radiation law by calculating the oscillator energy using the assumption of energy quanta, and then related the oscillator energy to the radiation energy using a relation derived from classical electrodynamics. Einstein derived the form of Planck's radiation law by assuming quantum mechanical processes of emission and absorption and requiring equilibrium. However, he could only infer the ratio between emission coefficients from Planck's law, while he invoked Bohr's postulate to equate the energy difference to Planck's constant times the radiation frequency. Satyendra Nath Bose remarked that all these derivations relied on a result from classical theory. He then proceeded to give a derivation of Planck's radiation law using only quantum mechanical principles. In Bose's derivation of Planck's radiation law, he assumes that radiation in a certain volume is composed of photons. The total energy is fixed, but the total number of photons is not. For example, a high-energy photon can be absorbed and then emitted as multiple low-energy photons. The photons can move in 3 dimensions, so its momentum vector consists of 3 components. The total momentum of a photon equals the photon energy divided by the speed of light, as is known from special relativity. The photon energy is given by Planck's constant times the radiation frequency, which was Einstein's quantum hypothesis. The photon's position and momentum correspond to a point in six-dimensional phase space, but for simplicity we only plot a two-dimensional cross-section of phase space, where the x and y components of the photon momentum are plotted. The phase space is coarse-grained into cells, and the volume of each six-dimensional cell is given by Planck's constant cubed. Planck's radiation law gives the radiation energy density for a certain frequency. Therefore, what we're interested in is the number of photons that lie within a certain frequency interval. In three-dimensional momentum space, this frequency interval is described by a spherical shell with some finite thickness. We can calculate the volume of this shell by multiplying the shell's surface area with the shell's thickness. We can express this volume in terms of frequency by using the relation between photon momentum and frequency. To find the number of phase space cells inside this frequency interval, we take the momentum shell volume, multiply it with the real space volume of the box, and divide it by the phase space volume of a single cell. To take into account the fact that radiation is polarized and therefore has two components, we multiply the number of cells with a factor 2. All photons that lie within this frequency interval are in some way distributed across the different phase space cells. We can count the number of cells that have a certain amount of photons. In this example, there are 8 cells which have 0 photons, 3 cells which have 1 photon, 3 cells which have 2 photons, and 2 cells which have 3 photons. We can find the total number of photons in this frequency shell by adding together all the photons in these phase space cells. To find the total radiation energy in the box, we multiply the number of photons in a certain frequency shell with the energy of a single photon, and then sum over all frequencies. We can rewrite this expression in terms of the number of cells that contain a certain amount of photons. Now one may ask, how are all these definitions and equations going to help us derive Planck's radiation law? Recall that according to Boltzmann's statistical mechanics, a system will settle into the macrostate that has the highest number of microstates, where each phase space configuration counts as a different microstate. So to find out how the photons will be distributed over different frequencies, we need to calculate how many microstates yield the same distribution. The distribution with the most microstates is the most likely macrostate and should therefore correspond to Planck's radiation law. So to find the total number of microstates for a given radiation distribution, let's first see in how many ways we can distribute a given number of photons over the phase space cells in a certain frequency shell. If we must distribute indistinguishable particles in a way that a certain number of cells have a certain number of photons, then the number of different ways we can distribute the photons equals the number of cells factorial divided by the factorials of the number of cells that have a certain amount of photons. We will see later that the assumption of indistinguishable particles is crucial in obtaining the correct radiation law, even though Bose did not explicitly mention this in his publication. The expression can be approximated using Stirling's approximation. To find the total number of microstates which correspond to the same radiation distribution, we multiply the multiplicities for the different frequencies. To find the radiation distribution that will occur in practice, we need to find the state with maximal multiplicity, under the constraint that the total energy has some fixed value and that there is a certain number of phase space cells per frequency. To solve this optimization problem, we define a cost function, which consists of the quantity that is to be optimized and the Lagrange multipliers for the different constraints. After cancelling some terms, we can optimize the expression by setting the derivative of the cost function equal to 0. We can calculate the derivative straightforwardly and then find an expression for the number of cells that have a certain number of photons of a certain frequency. The expression we found contains a parameter whose value is yet to be determined. To find this value, we recall that if we add all the numbers of cells which have a certain amount of photons, we find the total number of cells for a given frequency, which we know. So we calculate the sum, equate it to the total number of cells for a given frequency, and then solve for the parameter A. We can now find an expression for the total radiation energy in a certain volume by adding the energies of all photons. We plug in the expression for the number of cells that have a certain number of photons. The summation can be calculated more easily by writing it as a derivative of a summation we already calculated before. We can calculate the derivative of this sum and substitute the value that we found for the parameter A. The radiation energy density is defined as the radiation energy per unit volume per unit frequency. When we plug in the expression for the total radiation energy that we found, we obtain something that already looks a lot like Planck's radiation law. The only thing we need to do is demonstrate that the Lagrange multiplier beta has the correct value. We use Boltzmann's expression for entropy and plug in the value for the multiplicity that we found earlier. When we plug in the expression for the number of cells that have a certain amount of photons, we can rewrite one term using the total number of cells for a certain frequency, and the other term using the total radiation energy. The temperature is defined using the derivative of entropy with respect to energy. When we calculate this derivative, we find that the Lagrange multiplier beta equals 1 over Boltzmann's constant times the temperature. When we plug this into the expression we found for the radiation energy density, we obtain Planck's radiation law. Therefore, we have derived Planck's radiation law from purely quantum mechanical principles. When Einstein received Bose's derivation, he recognized its importance and subsequently published 2 papers where he extended Bose's logic from photons to atoms and molecules. Other scientists remarked that in Bose's derivation, the photons were assumed to be indistinguishable, even though it wasn't mentioned explicitly. Einstein agreed and proceeded to compare the cases of distinguishable and indistinguishable particles. Einstein's method of deriving the radiation energy density differs somewhat from Bose's derivation. In Bose's derivation, we calculate for a given frequency shell the multiplicity of the most likely macrostate. In Einstein's derivation, however, we assume that this multiplicity is practically equal to the total number of ways in which we can distribute the photons over the cells in a given frequency shell. This simplifies the analysis, because we only need to optimize the distribution of photons between different frequency shells, rather than the distribution between phase space cells within a single frequency shell. So in Einstein's derivation, the question is in how many different ways we can achieve a given distribution of photons between the frequency shells. What constitutes a different way will depend on whether we assume photons to be distinguishable or indistinguishable, as we will see in the following. As a simple example, consider 2 frequency shells which have 3 and 4 phase space cells each. Let's consider a macrostate where there are 2 photons in the first frequency shell and 3 photons in the second frequency shell. Now the question is, in how many different ways can we distribute these 5 photons over the 2 frequency shells such that there will be 2 in the first shell and 3 in the second? Let's assume the photons are indistinguishable, so we cannot label them to tell them apart. First, let's calculate the total number of ways in which 2 photons can be distributed among 3 cells. We represent a distribution among 3 cells with 2 partitions. The photons left of partition 1 are in cell 1, the photons left of partition 2 are in cell 2, and the remaining photons on the right are in cell 3. So if we have 2 photons and 2 partitions, we have 4 slots to which we can assign either a photon or a partition. For the first photon or partition, there are 4 slots to choose from. For the second, there are 3 slots to choose from, etc. So there are 4 factorial ways to arrange the photons and partitions among the 4 slots. However, because the photons are indistinguishable, we've counted several identical configurations multiple times. so we need to divide by the amount of times a single configuration is counted. Moreover, if we move a partition and its corresponding photons around, we also end up with the same physical configuration, so we also need to correct for this multiple counting. Therefore, we find that there are 6 different ways to distribute 2 identical photons over 3 phase space cells. Similarly, we calculate that there are 20 ways to distribute 3 identical photons over 4 phase space cells. For each one of the 6 configurations for the first frequency shell, there are 20 possible configurations for the second frequency shell. Therefore, the total number of ways to distribute 5 identical photons in this way over the 2 frequency shells equals 6 times 20, which is 120 ways. Now let's see how the situation changes if the photons are distinguishable. That is, we can label the photons to tell them apart. To randomly divide the photons among the frequency shells, we can randomly permute the 5 photons. There are 5 possible choices for the first photon, 4 for the second photon, etc. So there are 5 factorial ways to order the photons. To correct for double counting, we must also count the number of ways the photons within one frequency shell can be permuted. When we do this for all frequency shells, we can calculate the number of ways to distribute the photons over the frequency shells. Once we have assigned certain photons to a frequency shell, we must assign those photons to the phase space cells belonging to that frequency shell. For each of the 2 photons, there are 3 choices available, so there are 3 to the power 2 possible ways to distribute the photons among the phase space cells. The same goes for the second frequency shell. So to find the number of ways in which we can assign to each frequency shell a certain number of photons, we take the number of ways in which we can assign the photons to the different frequency shells and multiply it with the number of ways in which we can distribute the photons in one frequency shell among its phase space cells. In case the photons are distinguishable, we can distribute the photons in many more different ways than if the photons are indistinguishable. So we found 2 different formulas for the multiplicity of a certain distribution of photons among the frequency shells, depending on whether the photons are distinguishable or not. We can find the entropy of a certain distribution by taking the logarithm of the multiplicity. To find the most likely way that photons are distributed among different frequencies, we must maximize the entropy under the constraint of fixed energy. So we take the derivative of the cost function, set it equal to 0, and solve for the number of photons in a given frequency shell. We plug in the number of phase space cells in a certain frequency shell, the expression for the radiation energy density, and the value of the Lagrange multiplier. Then we see that if the photons are indistinguishable, we obtain the correct Planck's radiation law. If we assume the photons are distinguishable, we obtain the only approximate Wien's radiation law. Einstein applied the same derivation to particles such as atoms or molecules instead of photons. In this case, we want to describe the distribution of particles as function of energy instead of frequency. Instead of counting the number of phase space cells for a certain frequency, we count them for a certain energy, which yields the density of states. Moreover, whereas the number of photons was allowed to change, we assume that the number of molecules or atoms stays fixed. So we have to add an extra constraint in the cost function that we optimize. When we set the derivative of the cost function equal to 0, we can solve for the number of particles that have a certain energy. We define the chemical potential and we plug in the value for the Lagrange multiplier beta. Then, for indistinguishable particles, we get what is now known as the Bose-Einstein distribution. For distinguishable particles, we obtain the Maxwell-Boltzmann distribution. So we see that to get the correct formula for the radiation energy distribution, we must assume that photons are indistinguishable. If we don't make this assumption, we obtain Wien's radiation law, which is only accurate for high radiation frequencies. To get an accurate prediction for low frequencies, we must assume that the photons are indistinguishable. However, We already knew of another radiation law that is accurate in the low-frequency regime. This is the Rayleigh-Jeans law, and this law was derived using classical wave theory. Therefore, it appears that the indistinguishability of particles is related to the particles having a wave nature, as de Broglie proposed. But why would indistinguishability be related to a wave nature? Consider two particles that occupy the same cell in phase space. This means they have the same position and the same momentum. And according to de Broglie's matter-wave hypothesis, having the same momentum means having the same wavelength and the same oscillation frequency. This means the wave functions of the two particles can interfere coherently to yield a wave function with increased amplitude. When one particle moves to another position, then the wave amplitude splits in two. But when a wave gets split in different components, for example when it gets partially reflected by a surface, it doesn't make sense to ask which part of the amplitude has been split off. So the indistinguishable nature of particles becomes apparent when their wave functions can interfere coherently. For example, gas particles will noticeably deviate from classical Maxwell-Boltzmann statistics and start obeying quantum mechanical Bose-Einstein statistics when the temperature of the gas is decreased to the point where the wave functions of the particles start overlapping and interfering coherently. So we've seen how the quantized nature of radiation and of particle motion has been demonstrated experimentally, and how it can be explained theoretically using the concept of wave-particle duality. But if particles have a wave function, the next obvious question would be, what wave equation describes the dynamics of this wave function?